going to run another experiment, and then we're going to go over and do the problem of this on the board also. So I'm going to turn on the faucet, and you can turn on the faucet at any rate that you want. You can turn it on full power, or you can turn it on like half power, and then you can do a physics problem with this. First, I'm going to determine how many seconds it takes for a certain amount of water to fill up, so that I can calculate the volume flow rate of the water coming in. Okay, so I have here a 100 milliliter graduated cylinder. Okay, I'm going to put it there, time how long it takes to fill up 100 milliliters of water. Okay, it took approximately 1 minute and 20 seconds. Okay, 1 minute and 20 seconds. The next thing I'm going to do, I'm going to measure, so let's write that down. And then the next thing I'm going to do is measure the diameter okay, that one is 1.8 centimeter diameter. And then I'm going to measure the diameter of the water at a certain point. You will notice that when you see a column of water, the diameter starts getting narrower and narrower. So I could choose any point along the path and measure its diameter. Let's choose a certain distance, like 12 centimeters down. 12 centimeters down. Okay, so the diameter of the water has pretty much reduced to 0.8 centimeters. I go down, the more the column of water will get narrower and narrower. Okay, now we are going to go over to the board and we're going to solve this as a physics problem. Okay, thank you very much. Now let's do the problem related to the faucet problem that we did. This is the information that we gathered. We had a faucet. The velocity was coming down at a certain velocity V1. The velocity here is certain velocity V2. The height of the column of water is 12 centimeters. So we found out that it took 1.20 seconds to fill 100 milliliters of a graduated cylinder. I think when I was doing the video on the actual experiment, I told you that it took 80 seconds. That is wrong. It wasn't 1 minute and 20 seconds that it took. So it was very, very quick. So it's not 80 seconds, it's 1.20 seconds that it took to fill that amount of water. The height of the column of water, 12 centimeters, the diameter of the top, 1.8, the diameter of the bottom, 0.8. So let's treat this as a physics problem. Let's say you are given this in a homework or test situation. You are told that the diameter of the top is 1.8. You are told that the height of the column of water is 12 centimeters. You are asked to find what the diameter of the bottom is. It's not given to you. And then you're also given that it fills up 100 milliliters in 1.20 seconds. So how would you be able to calculate for the diameter of the bottom? So here's what we're going to do. We're going to use Q is the volume flow rate, volume divided by time. So let's first calculate what that is. 100 milliliters in 1.2 seconds. Then we convert 1 milliliter is 1 cubic centimeter, and then 100 centimeters is 1 meter. Then we cube this. This will convert the volume flow rate to units of meter cubed per second. So we're going to have 100 divided by 1.2, that's the time, divided by 100 to the power 3. Now we can use the fact that Q is equal to A1 V1, so we don't know the velocity with which the water is starting to go down from the top, but we can calculate that because we are given the diameter of the top. So we have 8.33 times 10 to the negative 5 is equal to the diameter of the top pi times the top diameter squared, 0.018 squared. So convert this to meters again, 0.018 meter, divided by 4 times V1. So take the answer that we got per second. So that's the initial velocity with which the water is going to be coming down. Okay, next what are we going to do? Now we're going to use Bernoulli's principle. So let's go to the Bernoulli equation. 2 squared. We could put the xy axis here at the bottom. so that the H bottom is 0. And then we can assume that the pressure pushing down on the top of the water here is pretty much atmospheric pressure because it's open to the atmosphere. So the pressure pushing down here, that's going to be roughly about atmospheric pressure, maybe slightly higher, but not too much higher. And then the pressure at the bottom pushing up on the column of water is also atmospheric pressure. So these two cancel each other, okay? So they're both atmospheric pressure. Then we can cancel the density of the water. Density of water, density of water, density of water. Now we have GH top plus half V1 squared is equal to half V2 squared. So we can use Bernoulli's equation to calculate the velocity of the water at the bottom, right? We can multiply everything by 2. We have 2. Then 2 times 9.8. The height of the column of water would be given to you. So 0.12. V1, we already calculated that, but we just got to square it, right? 0.327 squared. Now we calculate what V2 is, right? Okay, so pretty much the velocity has gone from 0.3 to 1.5. The velocity has gone up by a factor of 5. Now is our last step. Predict what the diameter of the column of water will be over here. So we can use this equation again. We already know the volume flow rate is 8.33 times 10 to the minus 5. This time, we don't know what the diameter of the bottom is. Diameter of the bottom. We're supposed to predict that. This one, we're going to put V2, right? So we're using this equation all over again. This is the same number. V2 is 1.57. 1.57. Right? So just take this, multiply by 4, divide by that, and then calculate that whole thing. Equal to diameter of bottom squared. Now we take the square root of that. Meters. Okay? Then we can compare that to our experimentally measured result and see if this method is actually working. You see that when I measured the diameter of the bottom, it was 0.8 centimeters. Okay? That's pretty much what I got here. If you move over the decimal twice, that's 0.82 centimeters. So of course, it's not an exact because when I'm using the vernier to measure the water, the numbers are not exact and everything, but to get there that close is actually pretty surprising. We ran the experiment pretty rough, though I wasn't very precise on the numbers, but we actually got the actual theoretical equation to agree with the experimental measurement. So that is actually pretty impressive. This way of solving these kind of problems actually is working. So in an actual problem, the problem could give you this diameter, and it could give you that diameter, and it could ask you what was the height of the column of water. Or it could give you this diameter, that diameter, and the height of the column of water, and it can ask you what was the volume flow rate of the water. So any one of these quantities might not be given to you. So the problem might ask you to solve for that unknown quantity, okay? So I hope this helps and it gives you a good illustration of a Bernoulli's equation problem. Thank you very much.